So we are going over derivatives and graphing. Concave up, concave down, inflection points, critical points, all things needed for graphing. We're looking at a lot of examples, and then we'll end on optimization. Okay. So let's go through the graphing part that comes with derivatives. First thing we want to talk about is, remember when the tangent line is negative, okay, or has a negative slope, that means the function is decreasing. Okay, but when there's a positive slope, that means it's increasing. So when the derivative is less than 0, remember that means you're decreasing. When the derivative is greater than 0, that means you're increasing. And when the derivative actually equals 0, what does that mean?
It means it's a point of inflection.
Yes, it's a point of inflection. It's either going to be, well, not inflection, but a point of
concavity.
Not concavity.
Heck.
Extrema. That's the word.
Oh.
A max or a min. Because when you say concavity, you're talking about second derivative. You don't want to get them mixed up. Okay, so first derivative deals with increasing, decreasing, your critical points, extrema. Okay? So, that's note. Should we take smart notes? Okay, let's take a look at this example. It says, consider f of x equals the ln of x to the 4th plus 1. You have to find the value of f of 0. Not to be confused with f prime of 0. For part A, what am I doing? Solely.
Plugging 0 to x.
Plugging 0 to x into the original, right?
Yes.
So this becomes the ln of
1.
And what's the ln of 1?
10.
No.
Ln of 1 is 0.
Ln of 1 is 0. Not quite
I
sure.
thought it was 10.
Not quite sure. Ln of 1 is 0. Okay, think e to what power gives you 1, and that's 0. Then it says find the set of values for which x, find the set of values of x for which f is increasing. That means I need to find the derivative. Okay? I need to set it equal to 0, so then that way I can find where it's neither increasing or decreasing, and then we make our line, our number line. Okay? So, to do the derivative of this function, what rule am I using?
Chain.
So I do the derivative of the outside, which is,
1 over x.
but I don't write an x, I write,
And x to the 4th plus 1.
then you multiply by
4x cubed.
4x cubed, which is the derivative of the inside. So my derivative becomes 4x to the 3rd all over x to the 4th plus 1. Now, real quick, can I cancel out the x to the 3rd with the x to the 3rd at the bottom and just make it 4 over x plus 1?
No.
Good. You can't cancel like that.
How can you cancel?
When things are being multiplied together. So if this was like x times x to the 4th plus 1, then you could cancel out an x because it's being multiplied. I have to set this equal to 0. Now, because this turns into a rational function, remember when you set rational functions equal to 0, you're really only setting the numerator equal to 0. Very good. So then I divide by 4. Still 0. Take the cube root, so my critical point is
0.
0. Okay? I make my number line. I put 0 on it, and then this is when I do the...
Plug in a number bigger and small.
Very good. What's a number smaller than 0?
-1.
Bigger than 0?
1.
And where do I plug these values into?
The OG function.
Not the OG function,
Derivative.
the first derivative. Because remember, I'm trying to figure out where the function's increasing or decreasing, so I got to plug it into the derivative. Okay? So I'll plug -1 into the derivative. I'm not concerned about the number. I'm concerned about the sign of the number. So when I plug in -1 here, my numerator is going to be,
Negative.
my denominator is going to be,
Positive.
and a negative over a positive is a,
Negative.
when I plug in +1, my numerator is,
Positive.
my denominator is,
Positive.
which gives me a,
Positive.
and remember, we plug these numbers into the derivative because the derivative lets us know if we're increasing or decreasing. So since it's positive, everything to the right of 0, that means the set of values for which f is increasing is what?
0 to infinity.
Parentheses or brackets?
Parentheses.
If it's a bracket, that means I'm including it, but at 0, remember, that is a extrema.
Could you say that you can include 1 and 1 comma infinity and make a bracket around 1 and then parentheses around infinity?
But then we're forgetting about things like if I make only 1 to infinity, that means I'm forgetting about like 1/2, 1/3, which still work. Yeah.
0.00001.
Or those, yeah. So, if you notice, well, first off, questions on this. Negative to positive slope means what? Negative to positive means I have a what?
Concave upwards.
What is that called? What is this called?
Upwards parabola.
I describe it a different way. Describe it.
Static parabola.
No. Remember, this is just one piece of the function.
Oh, relative minimum.
It's a minimum. There we go. It's a minimum. This is not a quadratic. Remember, it's a natural log function. So yes, it is a minimum. Remember, when you go from negative to positive, you have a relative minimum. When you go positive to negative, you have a relative maximum. Okay, this is what the first derivative test tells us. When we do derivatives, set it equal to 0 and make our number line, that is the first derivative test. Okay? So negative to positive, min, positive to negative, make a max. And then, of course, to actually find the point, you take that critical value and plug it into the original function. So we're looking at B and D to find the intervals where the function is increasing or decreasing. I also added in to locate the extrema. So remember, you need to find the first derivative anytime you're looking for extrema or increasing or decreasing. What's the derivative of B?
4x cubed minus 4x.
Minus 4x. So then you have to set that equal to 0. When you set it equal to 0, you need to go ahead and factor. There's a GCF of a 4x, leaving you with an x squared minus 1. Then you'll set both factors equal to 0. So that's 4x equals 0 and x squared minus 1 is equal to 0. So then you're going to have here 3 critical points.
Do it.
Where are they located?
0, -1.
Okay, so there's something happening at each of those points, whether it's a max, a min, it might not be anything. Okay, but we need to take those points, we need to put them on a number line. That's -1, that's 0, and that's 1. So then that is 1, 2, 3, 4 intervals that I need to check. -2, -1/2, +1/2, and +2. I need to check these numbers that are in between each of these intervals, and I plug them in where?
You plug them into that derivative.
Into the derivative, which is right here, that 4x to the third minus 4x. When I plug in -2, that's going to give me a -32 plus 8. Is that positive or negative?
Negative.
Negative. When I plug in a -1/2, that gives me a 1/8. Okay, 4 times 1/8 is a 1/2. Then negative and negative make a positive. So what's actually happening in between -1 and 0?
Positive.
It's positive. When I plug in a +1/2, that gives me a 1/8 minus, 1/8 times a 4, that's 1/2. Then I have a 1/2 minus a 1/2. Did I do that right?
Yes. No, wait, it's 1/2 minus 2.
Oh, it's 1/2 minus 2, positive or negative?
So that's a neg. That's a negative.
That's a negative. And then a +2, do they give me a positive number or a negative number?
Positive.
So I know that we are increasing from where to where?
-1 to 0 and from 1 to infinity.
Okay, and what do I put around these?
Parentheses.
Very good. And then I'm decreasing everywhere else, correct?
Yep.
Okay, so that's negative infinity to -1, and then from 0 to 1. Perfect. So then what is happening at -1? Is that a max or a min?
Okay, -1.
-1.
Yeah, it's a min.
It's a min, because I'm going from negative to positive. At 0, that's a
Max.
max, and then at -1, that's a what? It's a min. And how do I find the point location?
Plug it into the original.
Plug it into the original. So -1 to the 4th power is a +1.
So you plug that into the original.
Yes, all of these points into the original to find any point that's on your original function. So then that becomes 1 minus 2, which would be a -1. So -1 is a min. When I plug in 0, that's going to give me a 0. When I plug in 1, it's going to give me a -1. That's how I do that one. I wanted to give you B because B was an easier one.
Oh.
Okay? D was the one that was a little bit more involved because the one more involved is a rational function.
Which means low to high and high to low, low, and that's a big thing.
So that had that to incorporate the quotient rule when I do the derivative. And on top of that, when I set the derivative equal to 0, not only do I have those critical points, but I'm also going to have to deal with asymptotes as well.
Oh.
Okay. Do not forget, whenever you have a rational function, you have to take into account your vertical asymptotes as well, because those are points of discontinuity. It's not defined at those values. So those also need to be on our number line. So I'm going to go ahead and swing to a brand new page. So in that way I can,
Those are called rational functions.
when you have a function divided by another function. So let's do the derivative. How's it go?
Low. D high.
Which is?
3x squared.
Minus
High.
D low.
Which is?
X.
All over?
Hello.
I am going to leave it in this factored form just in case if anything happens to simplify. I wanted the factored form to see it. So that's going to give me a 3x to the 4th minus a 3x squared minus a 2x to the 4th all over x squared minus 1 squared.
Can't we just take one of the x squared minus 1s from the top and the bottom?
I cannot cancel this and this. Why not?
Subtraction.
Because I have that subtraction there. And because of that subtraction with a whole other term, if that second term does not have an x squared minus 1, I cannot cancel them out.
If we wanted to cancel them out, we'd have to split them, wouldn't we?
That won't help our situation considering that I got to set it equal to 0.
I'm saying like if you
minus 3x.
if you didn't have to rationalize or anything, and you just wanted to cancel out, you'd have to separate it.
Correct. So this is my derivative here. Okay? I can take an x squared out of the top, but it's not going to leave me with an x squared minus 1 on the bottom, or left over. So then I'm going to continue to move forward by setting the derivative equal to 0. Since this is a rational function, I'm basically setting the numerator equal to 0. So that's x to the 4th minus 3x squared is equal to 0. I can divide everything by an x squared, right?
Yes.
Yes.
I cannot divide everything by an
Oh,
x
because
squared.
of the subtraction.
About to say, what are you all talking about?
What do I do instead?
Silly gooses.
Take out an x.
Take out x squared. I factor it out instead.
Divide by x. We just went over this.
I just went over it, yeah.
That's what I thought.
I was just not looking. Right.
So I have x is equal to,
What were we talking?
0.
and x is equal to the
Plus
square
or
root of
minus 3.
Ooh, good job.
plus or
One
minus.
thing I forgot that it has to be square root. Well, that ruins all my plans.
Okay. So I'm going to have a 0 on my number line. I'm going to have a negative square root of 3. I want to have a positive square root of 3. But I also need to have what on this?
Yeah,
The
in between
asymptote.
the asymptotes.
Which are, and review, how do I find the asymptotes?
Oh,
Vertical?
for the
said
yeah,
the
for the
bottom
vertical
equal
asymptote,
to
but the
0.
denominator equal to 0. And for the horizontal, you just compare
Look at
the
the powers. on the
yeah
top and
the
the bottom.
coefficients.
That's right.
Uh,
So when I take the square root, what do I get?
plus
Plus
or
or
minus
minus
1.
That's 1.
So even those have to go on your number line. And hopefully you guys do know that square root of 3 is larger than 1.
It is.
Yeah.
Because what's the square root of 1?
1.
And isn't square root of 3 bigger than that?
Yes.
Yes.
Okay. So you gotta test out some intervals here.
Griffin did.
You only need
Well,
the,
let's just
the
plug them
vertical.
So we did our test points on our number line. As we can see here, we have a few things happening. Remember, at the asymptotes, it could continue to be decreasing because you have, it's getting really close to asymptote but never crossing or touching. So here we actually only have 2 extrema. Where do they occur?
Oh.
At square root of 3 and
Negative.
negative square root of 3. What's happening at positive square root of 3? Is that a max or a min?
Max. Wait.
It goes
Max.
negative to positive.
Oh, I was looking at
It's a min. And then a negative square root of 3, that is
Max.
a max. How do I find the y coordinate?
Plug it into the original.
You plug it into the original, and we'll just leave it there. Okay? But that's how you do increasing, decreasing, extrema. Questions?
None.
Remember to find any points, your points of extrema, you always plug the value into the original function. Alright? The second derivative dealt with our concavity as well as our inflection point. So when the second derivative was less than 0, it was concave down. When the second derivative was greater than 0, it was concave up. If you had a sign change and the second derivative equals 0, there was an inflection point. That's what causes something to go from concave up to concave down or vice versa. So it's a similar process as the first derivative test. You're just doing it with the second derivative, the whole number line thing and everything. Go ahead. Okay, so again, you're going to do the same process, except this time you just have to do it with the second derivative. You do your number line, and this time it's telling you about the concavity, concave up to concave down. All right, so we're going to do this particular problem, and I think, okay, we're going to do this particular problem, okay, and I'm going to leave you guys to it. Okay, I'm going to give you 6 minutes. Okay, here we go. So you have to use the fact that the first derivative is given to you to show that the second derivative is given to you. So to find the second derivative, which is asking you to do, you have to do the quotient rule for your first derivative. So that's low
I did it.
d high, which is a negative 48, minus your high, which is another negative 48x, d low. The derivative of your bottom is the chain rule. So, remember this is nothing but x squared as your outside function. So that becomes 2x, but you don't write an x, you write
X squared plus 12.
then you multiply by the derivative of the inside, which is a 2x. That's your numerator, all over your denominator squared. So that's x squared plus 12 squared, squared again. So then this becomes negative 48 x squared plus 12 squared. Two negatives make a positive. 48 doubled is
Negative 96.
96. 96 times 2 is,
Negative 192.
but it's going to be a positive because I have a negative and negative, which make a positive. So it's going to be 192 x squared. Then you have another x squared plus 12 on the inside.
Oh, we could have simplified a lot of it.
Mm-hmm. I don't know what you guys were doing.
We did the extremely long way.
Okay.
X squared plus 12.
We've been
That
through
was
this for
quick.
like 7 years.
I
and
just got done with it.
Jeez, no. That's I give you 6 minutes. After that, y'all should have, at the 4 minutes, y'all should have abandoned A and gone to B. Okay? Now look, if you notice every term, because here's your first term in your numerator, here's the second term in your numerator, and here's the denominator. Every term has an x squared plus 12 in common, right?
take it out.
So I can cancel out one x squared plus 12 here, this x squared plus 12 here, and this will turn into a 3. So then that becomes negative 48 x squared plus 12 plus 192 x squared all over x squared plus 12 to the third power.
Well, I guess we're just going to have to FOIL 48 so that we can make it like terms in 192.
Mm-hmm. Negative 48x squared plus, now yes, this one does end up being a little bit bigger. Oops, wrong thing. I meant to undo. Okay. What's 48 times 12?
576.
So 576 plus a 192x squared
Just combine like terms that heckin' thing.
and combine your like terms. So when I subtract this, that does give me what?
144x squared
I
minus
did it.
5.
I did it.
So you have a 144 x squared minus 576, and then you factor out. Now again, if you couldn't get this, doesn't mean that you stop here or you keep trying and struggling. You're timed. I still have to answer B.
Yep.
B says find the relative extrema of the function, which means I have to set the first derivative what?
Equal to 0.
Equal to 0. That's what we basically spent the first little bit of class doing. But B double I asked us to do what? That's when we set the second derivative equal to 0. When I do that, that leaves me with 144 x squared minus 4 is equal to 0. That becomes x squared minus 4 is equal to 0. So x is equal to plus or minus 2. I have to see if it's concave up or concave down, or sorry, there's a change of signs at those values. So again, I use test points. Where do I plug these test points into?
The second derivative.
The second derivative, because remember, the second derivative was going to tell me inflection points and concavity. All right? So I'm going to use these as my test points. My second derivative is right here. When I plug in -3 and I square it, that gives me a positive number. But at the bottom, when I square it and raise to the third power, it's still positive. When I plug in 0.
Yeah, that's going to be a negative on the numerator.
And a 1 on the denominator.
It's going to be positive.
So it's going to be a negative there. And I get the exact same value when I plug in a positive 3 like I got -3. So do I have inflection points?
Yes.
I have 2 of them. One at -2, one at +2. And how do I find the y coordinate of these inflection points?
You plug them into the first derivative.
Not the first derivative. The OG function. Anytime I'm ever looking for a corresponding y value, I always plug it into the original function.
Oh.
Okay?
Of 1, but at 1 cost.
All right. Questions?
Yeah, if we use up your markers so much, are we going to have to replace them?
No, I just got some new ones, so you guys are good.
Okay.
Now, the graph of the second derivative is shown. You have to write down intervals on which f is concave up and down. Give the x coordinates of any inflection points. Now, remember, this is the graph of the second derivative, which means what?
It means the
Wouldn't it just mean the inflection point is at -1, -4?
No, not -1, -4.
Okay, so we have, we concave,
The S and X value.
At the minimum, that's where the inflection point.
No.
okay, wait, it has to do with -3 and 1 because that's where we intersect, yep.
It does have to deal with these. Remember, this is the second derivative. This is the graph of the second derivative. What does this mean?
Oh, it means it's concaving downward.
No.
It's positive there,
It's positive here.
and then negative after -3,
It's
2, 1,
it's negative here.
and then it's positive after 1.
And it's positive here. Remember, this is your second derivative. So if you look at it in a number line sense, -3 and +1, that's where it goes from positive to negative to positive again. This is the second derivative, which talks about concavity.
Man, this is jarring.
So it's concave up from where to where?
From infinity, -infinity to -3, union 1 to infinity.
And it's concave down.
-3 to 1 parentheses.
There we go. Which means you have inflection points at
-3 and 1.
and 1. Because again, on the graph, if the graph is above the x-axis, it's positive. Below the x-axis, it's negative. And since this is the second derivative, we're talking about concavity here.
Oh, Lord.
Good to know it's the graph of the second derivative.
Mm-hmm. That's the main thing.
That's why it says the graph of the second. That same.
So your inflection points are at x equals -3 and x equals 1.
Wish you could see like a graph with like all the derivatives on it.
Oh, we're getting there. We're getting there.
Put it all
Okay.
together. Is this talking about my life?
We are going to put it all together looking graphing-wise before we move on to optimization. I'm going to give you guys 10 minutes to do this.
Okay.
Let's look at some features to start out with. What's our y-intercept?
-5.
All right, so I'm at 0, -5, so I know I have that. 1, 2, 3, 4, 5, 6, 7, 8. 4, 1, 2, 4, 1, 2, 4. or so I have a y-intercept at -5. What's my first derivative?
First
Oh,
3x
3x
squared
squared
plus 2x minus 5.
And my second derivative?
6x plus 2.
Okay. Let's start with my second derivative since it's smaller. When I set that equal to 0, it will be x equals a negative 1/3. If I do my number line real quick with the negative 1/3, I can plug in the test points of -1 and 0. I plug both of those orange test points into the
Second derivative.
to see if it's going to be
Concaving up or down?
okay. When I plug in -1, is that positive or negative?
Negative.
0.
Positive. Positive.
So I already know that I do have an inflection point at -1 in some other coordinate, some other y coordinate, and it's going to be concave down from -infinity to -1/3, and concave up from -1/3 to infinity. Where is that inflection point? Anybody find it?
You just have to plug those numbers into the original function,
I
correct?
do have to plug into the original, and so we're going to get a -88/27. Okay,
That's about 3-ish.
it's about 3.
3-ish, yeah.
About 3-ish. Okay, so -1/3 and a little bit more than -3. So there's my inflection point right there. Okay, let's set my first derivative equal to 0 to figure out where my extrema are. Okay, when you guys factor this, hopefully you factored it correctly. You got 3x plus 5 and x minus 1.
Nope.
Should have. So you should have got negative 5/3 and positive 1.
I look at danger in the eye and I say, you know what? Screw me over right now.
You make your number line with -5/3 and 1. I'm going to plug in these green test points where?
-2, 0, 2.
Where am I going to plug them into?
Oh.
The first derivative. Positive or negative when I plug in -2? Positive. When I plug in 0? When I plug in +2? So that means I have a turning point at -5/3 and some value and 1 at some value. Did anybody find the coordinates for that?
Yes.
Which
I
one?
have 1,
Okay.
1, -8.
1, -8. So is that a minimum or a maximum?
That's a minimum.
That's a minimum. So 1, -8. There's a minimum here. So there we go. I had a turning point. I should be concave down. Boom, boom, boom. Roughly. Okay. And then there's my minimum of 1, -8. I have a maximum at -5/3 and
I got 320/27.
it's big.
We got 40/27.
40/27. 40/27. That's a little bit more than
2, 1.
a little bit more than 1.
Yeah.
So -5/3 and a little bit more than 1 should be right here. So then this should be my max, which means this should be concave down here. So now we have this part. The only thing I need to know are my x-intercepts, which I really can't call it here because this is the cubic. I can't factor by, can I factor by grouping?
No,
You can do that?
Factoring by grouping is a way to
Oh.
factor a 4-part,
Pull out
since always.
yeah.
You can pull out an x squared,
X squared, so it's x plus 1.
x plus 1, and then
you
from
can pull out a -5, so we have
x plus 1 again.
x plus 1 again, yeah.
So then it would be x squared minus 5, and then x plus 1. So I have an x-intercept at -1, and then I have an x-intercept at plus or minus the square root of 5, which is a little bit more than 2.
Oh, okay.
And there's your function.
I forgot how impressive this can be at times when it's done right.
So my x-intercepts were located at -1, 0, positive square root of 5, 0, and negative square root of 5, 0.
How did you do the grouping thing?
You group the first two, you group the last two, you take the GCF out of both groups, and then that's what these two were in the orange over here on the left. And since they both have an x plus 1 in common, that's one of your factors. The ones on the outside is your other factor.
So first derivative, maximum, second derivative, inflection points,
And concavity.
and your cavity. And then from the original, you get where the x-intercepts are.
Yep. And y-intercepts.
Godek.
And the y-intercepts.
I don't know, best finish tomorrow.
You have 6 concatenates.
Alright?
Oh, I remember this one.
Alright, this one is a old problem. I pulled it from an old IB exam. You have a function given here. The gradient of the curve has its maximum point at B, its minimum point at D. The tangent is horizontal at points C and E. Remember, if the tangent is horizontal, that means what?
It's at zero.
Inflection.
No, it's zero.
What's zero?
The tangent.
The derivative.
The derivative. Remember, if it talks about a tangent line is horizontal at C and D, remember the derivative touches the graph at one point. So if you have a tangent, that means that it's talking about the derivative, the slope of the derivative. Okay? So complete the table by saying whether the first derivative is positive or negative. Same thing with the second derivative. From A or B, A to B. Is that positive? The first derivative is a positive or negative?
Positive.
It's positive because the slope of any tangent line is
Positive.
positive. What about from E to F, the first derivative?
Negative.
Very good, because any slope of any tangent line is going to be negative. Second derivative talks about what again?
Cavity.
So from A to B, is that concave up or down?
Concave up.
So that means it has to be.
Positive.
And what about from E to F?
Down.
So it's negative.
Plus negative.
Very good.
Nuggets.
Now take a look at this. You're given these different conditions, same graph. Which point represents a first derivative that's equal to 0, but a second derivative that's less than 0?
It should be series,
C.
right?
It's C.
So it's C.
It has to be, what one?
Wait.
So what's my answer?
C.
It has to be C, because it's saying the first derivative is equal to 0, which means it has to be one of the tangent line sides to be either C or E, and then more specifically, the second derivative has to be concave down. The only one that's concave down is C. E is actually a what?
Inflection.
It's an inflection point because it's going from concave up to concave
So
down.
that one would be
So
the second
E would-
derivative equals 0?
So, yep, this at E, it would be the second derivative is equal to 0. All right? What about the second condition where the first derivative is less than 0 and then where the second derivative is equal to 0?
D.
D, so you're telling me that the slope is negative and then also
No.
that it
It goes
Yeah.
from concave down to
Yeah.
concave
It
up.
can't also count
concave down to concave up. Very good. It would be.
I just guessed that.
All right, I want you guys to match these diagrams here on your desk. So remember the different features of what the first derivative is supposed to represent. The first derivative represents the slope of your tangent lines on your original function. So in figure 1 is all your original functions. So F1 was already done for you. If you notice, all of your tangent lines until 0 are negative, which means that your first derivative should have been less than 0 or below the x-axis until 0. Because after that, all of your tangent lines are increasing. They're all positive, which means it needs to be greater than 0. So anytime the first derivative is less than 0, that means you're going to be below the x-axis. And anytime it's greater than 0, means you're going to be above the x-axis. That's why D was the answer for F1. Because you have a x-intercept wherever there's an extrema, and then below and above. So if you look at option F2, you have an x-intercept at 0, so you're looking for the ones that have an x-intercept at 0, 0. There's only one option for that. What's the answer? E. Also, you can take a look. The slopes of the tangent lines are negative until 0, and then they're still negative afterwards, so it still needs to be below the x-axis before and after 0. What about 3? You have an extrema here, an extrema here, and an extrema here, which means you should have what?
3 x-intercepts.
I should have 3 x-intercepts, 2 before 0 and 1 after 0. Well, there's only one graph that shows that. Which one is it?
B.
It's B. You can also look. Negative, below, positive, above. Negative, below, negative all the way there, positive, above. So negative, positive, negative, positive. And then 4 is a all the tangent lines are negative, which means it should be a what?
Only
Everything below.
submerged.
So the only answer for that is
A.
A. C actually was above because that's your x-axis right there.
What?
So it had to be
Oh,
A.
that's-
Mhm.
I thought that was the x-axis.
See,
One other thing to think about is like you guys know that number f1, that was a quadratic, right? X squared. When you take the derivative of a quadratic, you get a what?
A linear.
A linear function. So that can help you. A quadratic that points up means you should have a line that's increasing. A cubic function, what's the derivative of a cubic?
Quadratic.
Quadratic. And since this is a cubic that actually is negative, you should have a negative quadratic. Keep those things in mind too when you're graphing as well. The same rules apply when you're looking at the first derivative and you're trying to get the second derivative. Okay? We're going to move on past the rest of the graphing, and I'll post the old video that actually went over the last three that I just skipped over, so you can take a look at those. We're going to talk about optimization and some of the things that you need to kind of keep in mind when you're doing optimization.
Oh boy.
Okay? This is where you're dealing with your word problems. You assign variables to given quantities and quantities to be determined, and if necessary, draw a sketch. You write an equation that is to be optimized. If it talks about you're looking for the maximum area, that means you need an area equation. If you're talking about the volume needs to be minimized, that means you need a volume equation. It needs to be in terms of two variables only. Then you find the values that make sense by basically taking the derivative of the equation that you created and setting it equal to 0. And then, of course, verifying if you have a max or a min using either the first derivative test or the second derivative test, which I'll talk about shortly. Sometimes you have to check endpoints because who knows, there might be a max or a min there. So we'll probably be able to get through maybe an example or two, and then I'm gonna post the rest. This one's pretty straightforward, pretty simple one. It says the sum of one positive number and twice a second positive number is 200. Find the two numbers so that their product is a maximum. Okay? So remember the steps. You need to assign your variables to your quantities or your quantities to be determined. What are we talking about here?
This one positive number and twice a second positive number, that needs to be assigned some variables.
Okay, so basically we're talking about two numbers here, right? All right. You can, if you want to, you can call them x and y. Okay. You know, one needs to be a positive number, and the other one needs to be what?
Another positive number.
That's what?
Double of x.
It's doubled the value. So you know that y is actually going to be equal to
2x.
2x. Okay? And it says this. Ooh, actually, hold on.
It's two separate numbers.
Actually, it is two separate numbers.
So it'd just be 2y.
Okay, so this one's actually going to be 2y. Okay? So then this is your second positive number. Now you know the sum of them has to equal what?
200.
So that's x plus 2y has to equal 200. So you have your first equation. Now the equation that we actually need to optimize, which is what we do in part 2, it says find the two numbers so that their product is a maximum. Product means what?
Multiplication.
So the equation we need to optimize is x times 2y to get, I'm going to make this A. A is going to represent the maximum. Okay, the product. So this is what you have. You basically have 2xy is equal to whatever it is that we're trying to maximize the product. Now you can't have this. Right now you have three different variables. You have to take this one equation that usually you have to create from another part of the question, and then you need to solve for one variable. Which variable you want to solve for?
X.
So if I solve for x, this is going to give me 200 minus 2y, and I use that to plug in 4x into the equation I'm trying to optimize. So then that's going to give me 2 times 200 minus 2y times y is equal to a. So basically I need to distribute a 2y to both terms inside the parentheses.
So 400y minus 4y squared.
And now your equation's in two variables, y, and then of course the product that we're trying to maximize.
And now you can take the derivative of
And now you can do the derivative. So you can do this as dA over dy to represent derivative. What is that? What's the derivative of 400y minus 4y squared?
400
Minus
minus
8.
8y.
You set that equal to 0. This is that third step. You basically are trying to find the value of y that's actually going to give you your product.
Let's just add a y, divide both sides by 8, and then y equals 50. Wait, no, is it 50?
Yeah, it's 50.
So y is equal to 50. So 50 is one of your numbers, okay? And so then if 50 is one of your numbers, you can find the other number by plugging in. And what do you get?
100.
100. So your two numbers are 50 and 100. You'll know for sure if 50 is indeed the value that will maximize your product by doing the first derivative test and plugging that into a number onto your number line. Okay? Give me a value that's to the left of 50.
51.
Okay, well that's to the right. Let's call it up
49.
and then 49. Okay? You want to plug both of these values into your
Derivative.
derivative. If I plug in 49 times 8 is going to be a value that is
It's still,
greater or less than 400.
It's going to be less than 400.
So then it's going to be positive. And if I plug in 51, that's going to be
Negative.
negative. Does that give you a maximum?
Yeah.
Yes, it does. You always want to make sure that you test just in case. I know I went straight into plugging the value in, but that's also how you determine for sure if that value makes sense. Okay?
What would you test it with?
You test it with, this is the first derivative test,
Oh.
and you use your test points.
Oh.
Plug them into the derivative. Yes?
Yes.
Coming back to you, maybe?
Kind of.
Yes.
Remember, you create
Oh.
basically two different equations. You use one of the equations to solve for one of the variables, and then you plug it into the equation you're trying to optimize. A rectangular pen is partitioned into two sections and built from 400 feet of fencing. Remember, fencing means what?
It's perimeter.
Perimeter is equal to 400.
Which means we got a square.
Okay?
Dang, farmers.
Careful, not so much, not when it's a partition like this. It's asking what dimension should be used so that the area will be maximized. So the equation I'm trying to optimize is the,
Area.
what's the area of basically a rectangle?
Like based on that.
We got length times width. Okay, so let's see what we're looking at here. Is this going to be my length or my width?
That's
With
where
Okay, so I have 3 widths. And what about my lengths?
you got 4 lengths.
So I'm looking at these individually.
Yep.
Okay, so then my perimeter, which makes up all of these, that means that's going to be 4L plus 3W has got to equal 400. You see how I have 3 different variables in the equation I'm trying to optimize?
yes.
I can't have that. So that means I need to solve one of these for a variable.
Yes.
Which one?
Let's do
L.
W.
No.
Let's do W, so then that way when I subtract over, alright, sorry, no, actually let's do L. Sorry. Either way, I just will try to make this simple for us because we no calculator. If I solve for L, I'll subtract 3W, and then I'll have to do what?
Divide both sides by 4. 4.
And at least this way, if I divide by 4, 400 divided by 4 is 100, and then this becomes 3/4 W.
But it doesn't say that they're partitioned equally. It just says they're partitioned. So do we?
Oh, into 2 different sections. Ooh, thank you. Good catch. Good
Dang
catch.
it, I screwed up.
It's okay. We can fix this. It's an easy fix because all I have to do is change these 4s into 2s. Just this. So this whole thing represents L, just like this whole thing represents L. 2L plus 2W, or 3W. 2L equals 400 minus 3W. Divide everything by 2.
This would be 200 minus 3 times W.
There we go.
There we go.
And then that I plug in for L. And this is the equation that I need to optimize. So that becomes 200W minus 3/2 W squared. What's the derivative of this?
200 minus 3, or, yeah, 3W.
3W? What do I need to do from here?
Something equals 0.
So that becomes 200 equals 3W. Divide both sides by 3 and W equals
200 over
200 over 3. Now let's make sure this is indeed a maximum. I know I can do it using the first derivative test by making our number line, but I did put a note up here to make sure that I mentioned the second derivative test. The second derivative test is something else that you can use, and in this case, it actually would be a little bit easier. What's the second derivative of the area function?
-3.
It will be just a -3. And the thing is that when you have the second derivative, if you evaluate the second derivative at the critical point that you found, since there is no variable here, the second derivative is going to be negative. Which means that if the second derivative is negative, it's greater than, it's less than 0, which means that there is going to be a maximum at that value. Okay? So I'll state that again over here off to the side. The second derivative test says that if the second derivative is less than 0, there is a maximum at that critical point. If the second derivative test is greater than 0, it's a minimum at that point. Okay? Now the second derivative test won't always work, especially if your second derivative ends up being 0. But in this case, since it was a constant, it still applied, and if it's less than 0, that means it was indeed a maximum. So my width is 200 over 3. How do I find my length? I plug it in. So then that'll be 200 minus 3/2 times W, which will be what?
Oh, a -100 and L equals 100.
L will be 100. And don't forget our units, so 100 feet and 200 over 3 feet. Covered a lot today, but remember with optimization, you have these 4 steps that you should follow. Create your equations, assign your variables, create your equation, especially the one that needs to be optimized. You'll solve one of the equations and plug it in. And then don't forget to verify if you have a min or a max. That'll kind of let you know if you've got the right number or not. Derivatives, and when it comes to the graphing, first derivative talks about increasing, decreasing, and extrema, where the second derivative talks about concavity and inflection points.